So 7.12 is over what's called the common ion effect, which just says that ionic compounds are less soluble in a solution that contains a common ion. So for example, let's take silver chloride here, which we know to be basically insoluble, but in reality everything is at least somewhat soluble. But we know that this silver chloride is basically not going to dissociate, but to some extent some will, whenever you try to dissolve it into pure water. However, if you were to try to dissolve some of this silver chloride into a solution that already contains some chloride ions, so there's already some chlorine present in this water, that's going to make this silver chloride here even less soluble than it was in the first place. And we can think about this through an equilibrium mindset here. Here is our silver chloride equilibrium expression, or equilibrium reaction rather. You've got your silver chloride, it's a solid. Since it's only slightly soluble, it's going to establish an equilibrium as it breaks into those two ions, the silver ions and the chloride ions. So this is an equilibrium, and just as Le Chatelier's principle would tell us, we can influence this equilibrium one direction or the other. Let's consider, for example, if we had the system at equilibrium and we were to introduce some additional chloride ions, that would push this equilibrium away from the stress we induced to this, which would push this equilibrium back towards the reactant side, which in this case is the silver chloride. Well, you're really doing the same thing in effect here. If you're trying to dissolve the silver chloride in something that already has a bunch of chloride ions in it, then this equilibrium was by default going to favor this left reactant side. Since that reactant side is the insoluble ionic compound here, you'll find that you could actually dissolve less ionic compound in something that already contains one of its ions. In other words, this is less soluble in this chloride solution than it would be in just water. So we can do a little bit of math here to prove it. So let's look at this question first. Zoom out just a little bit. We have calcium hydroxide, establish an equilibrium to make calcium and 2 hydroxide ions, and you're provided a KSP. Now this KSP is 1.3 times 10 to the negative 6th. That's small, that's to be anticipated. Not very much of this is going to dissociate. Most will remain in the solid form. We're wanting to calculate the molar solubility of it though when it's dissolved in water. So let's let our units kind of do some work here for us. I want the molar solubility. This means molarity, which is the same as moles per liter. I'm trying to figure out what's the maximum moles per liter of calcium hydroxide that will dissolve in water. Well, when you're working an equilibrium question, if you don't have a clue where to go, just start with your equilibrium expression. We know that the KSP expression for this guy's dissociation is KSP equals the concentration of the calcium 2+ ion times the concentration of the hydroxide ion, and that one will be squared due to our coefficient of 2 here. Now let's start thinking about what we know and what we could possibly solve for that would help us here. We know our value of KSP, that was provided to us, so that will be easy. We could calculate the concentration of calcium, we could calculate the concentration of the hydroxide, but if I look up here, I'm overall trying to find what's the molar solubility of that guy, the calcium hydroxide. So I'm going to let the coefficients here kind of help me. I can't directly solve for the calcium hydroxide's molarity in the solution because it's not part of my equilibrium expression. But I can solve for the calcium 2+ concentration right here. And since it's a 1-to-1 ratio, whatever that concentration of the calcium is must have all come from the dissociation of this calcium hydroxide, so they're going to be the same number. So let's just start plugging some stuff in here. I'm going to plug this 1.3 times 10 to the negative 6th in for my KSP. Get that out of my way. 1.3 times 10 to the negative 6th, and that is equal to, I want to solve for my calcium ion because his coefficient matches the calcium hydroxide's coefficient. So I'm going to determine calcium as X. Okay? Now I can't use Y or some other variable for hydroxide here because I can't solve an equation that has 2 variables in it. So I need to make a comparison of calcium to this hydroxide. Well, if you look, for every 1 calcium, there will be 2 hydroxides. So whatever the concentration of the calcium is, the concentration of the hydroxide will be twice that much, so it will be 2x. But don't forget to bring down your squared here. That squared is just part of the equilibrium expression. You've not yet accounted for it. So it's a little bit uncomfortable because some people think, well, I put the 2 here, do I really need them both? Yeah, you need them both. This is just part of the equilibrium expression, showing the relationship between these two. This here is showing that there's literally twice as much hydroxide as there is calcium. So let's go through and clean this up a little. 1.3 times 10 to the negative 6 equals x. Be careful, this is 2x squared. The squared is distributed through this whole quantity here. So 2 squared is 4, x squared is x squared. So really the right side ends up being x times 4x squared. So we clean this up just a little bit further now. X times 4x squared is 4x cubed. Okay? So now, we'll divide both sides by 4. We're trying to solve for x here. So this is, let's see, 3.25 times 10 to the negative 7th. Hopefully I did that right. Equals x cubed. Now to get rid of the cube, you gotta take the cube root of both sides. We'll take the cube root here. We'll take the cube root here. I'm gonna grab a calculator because I don't think I can do this in my head. And x turns out to equal 0.0688 molar. I'm gonna go ahead and write that in scientific notation as well. 6.88 times 10 to the negative 2nd molar. But let's stop and pause and realize what you just solved for here. You solved for the variable x, which up here we had established to be the concentration of the calcium. So this is the concentration of calcium that dissolved into this water. That's not what the question was asking for technically though. The question was technically asking what's the molar solubility of calcium hydroxide, and you solved for how much calcium's in the water. Well, where did that calcium come from though? Just like we said, it's a 1-to-1 ratio. So for every calcium that appeared in the water, it came from the dissolution, of the calcium hydroxide. So because it's a 1-to-1 ratio, this is a 1-to-1 ratio, this also provides the molar solubility of the calcium hydroxide. This is 6.88 times 10 to the negative 2nd molar calcium hydroxide. That means if you had 1 liter of water, you could only dissolve 6.88 times 10 to the negative 2nd moles of it. My unit got cut off there, so I'll kind of write it under here. Molar calcium hydroxide, still getting cut off, sorry. Okay? Now, this has nothing to do with the common ion effect. This is just us solving for a molar solubility. I just did all this because I want you to see this is not very soluble in water. That makes sense. It established an equilibrium. It has a small k value. All of this is good. Where it is important to consider, though, is now let's try to find the molar solubility of calcium hydroxide whenever you dissolve it in a, let's try that again, in a 0.5 molar solution of calcium nitrate. So there's already going to be calcium present in this solution. According to the common ion effect, that should decrease the solubility of this guy because you're disrupting the equilibrium by already having calcium present. But we have to stop and analyze this. The nitrate's not important right now. He's just there to cancel charge and to make sure this calcium dissociates and goes into the water. What is important is to register that for every 1 calcium nitrate, there's 1 calcium. So this means there's 0.500 molar calcium ions in that solution before we ever even start. So it might be easiest to try to rationalize this with an ice chart. And in this ice chart, let's just start with our equilibrium equation. You've got your calcium hydroxide breaking down into your calcium 2 plus and your 2 hydroxides. Okay? for an ice chart, you've got your initial concentrations, you've got the change in your concentrations, and then you've got your ending equilibrium concentrations. Oops, I'm trying equilibrium there. Okay. However, since this is a solid and it doesn't appear in the equilibrium expression, I really just don't care about any part of it, which is good because they never told me exactly how much calcium hydroxide I was starting with in the first place. But over here, before the reaction's even begun, you already have 0.500 molar calcium ions due to the calcium nitrate solution providing those common ions. Since nothing's happened yet, you don't have any hydroxide ions. So the change here, whenever I do dissolve some of this calcium hydroxide, I am going to gain some calcium here, because even though I suspect it's going to be less soluble, some of it's still going to dissolve. However much of it dissolves is going to result in a doubling of that amount of hydroxide due to the coefficient of 2 out front. So at equilibrium here, I'm going to have whatever 0.500 plus x is, and 2x for my hydroxide concentration. Now if we try to plug this into our equilibrium expression, this is going to require the quadratic formula, which is above AP Chem. So instead, we need to simplify this problem here. If the concentration was already 0.5 molar, and I'm adding just the ever so slightest amount of calcium in, because not very much is going to dissolve, then I am safe to make my assumption here that for all intents and purposes, this isn't going to change the concentration by calcium to any real degree. Now, in order to receive credit on your AP exam, though, you need to actually write out those words there. Something along the lines of, since KSP is so small, it is assumed that change in the concentration of your calcium ions is negligible. That allows us to clean this problem up. I only have one variable or one term here really that has an x in it, so this is going to be much easier to solve when I try to plug this into my equilibrium expression. So just as a reminder, our equilibrium expression was KSP equals the concentration of calcium times the concentration of hydroxide squared. KSP was still 1.3 times 10 to the negative 6th. Our calcium concentration, however, though, is whatever our equilibrium concentration was. We made the assumption that it's not going to change by any negligible or by any serious measurable amount. So we're going to leave this as 0.500. Our concentration of OH, though, was this 2x that we put here, which is still getting squared. So if we start trying to clean this up, this is 1.3 times 10 to the negative 6th equals 0.500 times, again, 2x squared is 4x squared. Now, 0.5 times 4, this left side didn't change. 0.5 times 4 is 2x squared. So we just do some algebra to finish this up. Divide both sides by 2. So 6.5 times 10 to the negative 7th equals x squared. Again, I'll grab a calculator. We're going to square root both sides to get that x by itself. 6.5 times 10 to the negative 7th square rooted. And this x turns out, oops, terrible x. This x turns out to be 8.06 times 10 to the negative 4th. Now let's pause and evaluate what we just solved for here. We said x is this tiny number. Up here, we said that x was our change in this calcium. Well, this change in the calcium is coming from however much of this calcium hydroxide dissociates. So once again, by finding this calcium, we found the molar solubility of our calcium hydroxide, this 8.6, while technically is the molarity of the calcium ions, it's still a 1-to-1 ratio. So this is also the molar solubility, 0.6 times 10 to the negative fourth molar calcium hydroxide. Now all of this to say, I need you to notice the common ion effect took hold here. On our first problem, let me see if I can zoom out a little bit. On our first problem, we found the molar solubility of calcium hydroxide to be 6.88 times 10 to the negative second. Not very much could dissolve, but that was the value. That's how many moles per liter would dissolve. Down here where there was a common ion though, your molar solubility is 8.06 times 10 to the negative fourth. It's 100 times less soluble. The solubility of this decreased due to the common ion. That was already in solution. In this case, that was the calcium. By that calcium already being present, the solubility of the calcium hydroxide had to fall.